Welcome in another video. Today we are going to discuss the average atomic mass and atomic radius of transition elements. So let's start with the average atomic mass. Here we have scandium with atomic number 21, as we can see here. So scandium 21. As you can see here, the average atomic mass in the unit of AMU, 45 AMU. Then we move to titanium with the average atomic mass of 47.9 AMU, vanadium with 51 AMU, and chromium, manganese, iron. As we can see that the average atomic mass increases. Cobalt as well, the average atomic mass is higher than iron. Then when we move to nickel, we can see that the average atomic mass is 58.7, which is less than cobalt, 58.9. But when we look at copper with the average atomic mass of 63.5 AMU, so here we have an anomaly with nickel, right? But generally, when we increase the atomic number, we increase the atomic mass, right? Or the mass number, right? Let me write the atomic numbers of these elements as well. Manganese 25, iron 26, cobalt 27, and nickel 28, copper 29. We can see this trend as well in the representative elements, right? So in sodium 2311, then magnesium in the same period we have magnesium 2412, and aluminium, the average atomic mass is 27 and the atomic number is 13. So as we can see here, when we increase the atomic number, the average atomic mass increases, right? So if we are to calculate the average atomic mass of nickel, we can calculate it from this relation. We can multiply the mass of the isotope times the percentage of its abundance. So for example, in the isotope nickel 58, we can write it like this: the mass 57.94 times its percentage, the percentage of abundance, right? So the percentage of abundance is 68.08, 68.08 over 100 plus the rest of the isotopes. So this is the first isotope, nickel 58, and we have nickel 60. So the mass of nickel 60 is 59.93 times its percentage of abundance, which is 26.22 over 100, plus nickel isotope 61, the 61 nickel isotope. So the mass of this isotope 60.93 times its percentage, which is surprisingly 1.140, plus over 100, of course, plus 61.93 times the percentage of abundance of this isotope, which is 3.635 over 100. So when you do the math, and when you calculate the average atomic mass of nickel, you get 58.70 AMU, or simply U, atomic mass unit. So because of the natural abundance of nickel 58 isotope with 68.08%, as you can see here, this leads to the average. This leads to the average atomic mass of nickel to be 58.7, and the rest of isotopes, you can see their natural abundance is a little bit low or small, as you can see here. So this is, for example, nickel 60 with 26.22%, and nickel 61 with 1.1%, and nickel 62 with 3.6%. So with this high abundance of nickel 58, you get an average atomic mass of nickel of 58.70. So how about the atomic radius? As we can see that the atomic radius decreases significantly, starting from scandium with 1.44 angstroms till chromium 1.17. So we can see a significant decrease in the atomic radius. But in case of chromium till copper, we can see that there is nearly no change in the atomic radius. The decrease in the atomic radius as we go from left to right actually makes sense, because the effective nuclear charge in case of sodium here is low. So the atomic radius of sodium metal, is high compared to chlorine. So as we go from left to right, as we go this way, the atomic radius decreases, right? Decreases. Since sodium metal has atomic radius of a bigger size than the chlorine gas here, right? The same trend can be seen in transition elements. So as we can see here from scandium till chromium that the average or the atomic radius of scandium should be higher than copper, because the effective nuclear charge of copper is higher than the effective nuclear charge of scandium. So atomic radius decreases as well, right? But there is a relative or nearly no change in the atomic radius starting from chromium till copper, and I'll tell you why. So starting from scandium till manganese, you can see that there is only one factor affecting the atomic radius, which is the effective nuclear charge. So as you go from scandium, you have here only unpaired electrons, single electrons. So for example, in the case of scandium, you have 3d1, titanium 3d2, vanadium 3d3, chromium 3d5, and manganese 3d5. Both of them have the same number of electrons in the 3d sublevel. So they will relatively have the same atomic radius. And actually, this is the case. As you can see here, that chromium and manganese both have the same. But what was expected for iron and cobalt and nickel and copper, that the atomic radius will decrease significantly. So it would be like, for example, 1.05 in case of iron, and in case of copper, 1.0 or whatever, 1.0. I'm just giving you some fantasy numbers. These are not actual numbers, right? So, and in case of nickel, like 0.9, and copper, for example, 0.8. Because I told you, when you go from left to right, you increase the effective nuclear charge, hence decreasing the atomic radius, right? But this is actually does not happen, does not take place, right? So what is the reason then? The reason lies in the repulsion between the electrons in the same orbitals. So as you can see in iron, you have, for example, the dxy orbital here. You can see these two electrons are repelling each other. So the atomic size increases, right? So when you increase, so you have two factors. One factor decreasing the atomic size, and another factor increases the atomic size. The first factor, which is the effective nuclear charge, which tries to decrease the atomic size, and the repulsion between the electrons tries to increase the atomic size. The same issue lies in cobalt and nickel and copper, right? So you can see here cobalt with two orbitals. They have two paired electrons, as you can see here, for example, the dxy and dyz or whatever orbitals. You can see that there are two orbitals, and these orbitals have paired electrons, and in the case of nickel you have three paired three orbitals with paired electrons, right? And in the case of copper you can see five orbitals with paired electrons. That's why the repulsion effect tries to oppose the effective nuclear charge effect, hence giving me a state of equilibrium. It's not an actual equilibrium, but you can see there is nearly no change in the atomic size. So as you can see, like the values, there is only a change of 0.01 angstroms, right? Or in the case of copper, it's similar to chromium and manganese, right? And that's it. If you like the video, please like, subscribe, and comment down below. See you in the next video. Bye.